Sorry, okay. I'll just test,
we worked in the group of three with me, Kuba and Janek, who couldn't be here today with us, and we worked with TCL about a project called Talking Face. What was our goal and how TCL wants to use this project? TCL wants to generate talking faces in the videos. In their app for their TVs, because they are producing TVs and they have their app with movies, and they want to add option to generate some talking faces with some characters from movies or cartoons and things.
For example, like an actor talking about the movie or something like that.
Yes, and they work with several models to generate talking face, and our goal was to pick one of them and improve performance of this model by dealing with some challenges that they have. We decided that we will work with the model called Set Talker. What was...
It was actually state of the art at the time, I think. Now it's been superseded by some other, but yeah.
It was like a year and a half ago. It was the state of the art model, and it works pretty well. But it has some problems with showing the emotions. I mean, all the emotions look the same at the video. So we wanted to show more emotions and prompt model with some emotions and generate different videos for all of them. So what's the problem? We want to do zero-shot video generation based on one image and an image of the person and audio file. We can also use a label describing the emotions from discrete set, but we don't have access to the text. We can generate it, use some model, but we don't have access to the text. We only have audio. So yeah, this is how Set Talker works. So this is encoder-decoder structure of the model. So we want to encode our image to extract some features from that. And then using audio, we want to generate those features for all of the frames. And based on that, we want to generate our video using 3D aware face renderer. Which is simply a decoder. So what are those vectors? From the single image, we can extract many features that tell us about camera angle, about light, but we don't want to change that during this generation process. So we will pass them to this renderer, and we only want to change two features. One is this beta. This is the expression vector, and the second one is pose vector. So this Set Talker model generates two of those features, and we want to change those small models. So this is XNet and Pose VAE. Okay, so this is the XNet training. I don't think that we should say a lot about it.
Yeah, it seems like not.
But I only want to mention one thing, that they use other models to generate losses during the training, and they assume that they don't have ground truth video. So they have to generate ground truth video from audio and image, and they use wave to leap to do it. So yeah, this is the assumption that they don't have ground truth video, which is not true in our case. We have ground truth videos, and yeah, here they have 3 losses. Each of that is computed using some other pre-trained model.
Yeah, actually, let me just point out that, like, if we forget about training, only this dashed blue box is important. So basically, the message from the slide is that audio gets encoded and mapped into betas, which are then fed into the phase reconstructor. Right, so the data sets that we used are, one of them is RAVDES, which contains videos like this with this as discrete set of 20 I don't remember how many emotions, and another data set we used, which is actually much more bigger. It's like, yeah, it's a 7,000 video data set, with also with actors saying phrases with different emotions and levels of intensity.
And those are the data sets to train models to detect the emotions, but we use it in other way.
Yeah.
We used those emotions as labels, and we wanted to generate those videos.
Yeah. Right, and basically our plan was to first verify that it suffices to modify those beta vectors in the model inference process to add those emotions, because like, we didn't want to invent a whole new model and train it from scratch. Yeah, we wanted to do that without increasing inference time, and yeah, for starters, we, like, for our purposes, we fine-tune the model for each emotion separately. So you have a separate model for adding anger to videos, for example, etc. And one of the approaches to a naive approach to adding those to modifying these emotion vectors was to basically calculate the use some other use the model that can extract betas from those emotional videos, and basically add some constant offset, for example. Yeah, so it's a very naive approach.
Yeah, we did it only to check whether it makes sense to change those betas. Yeah, are they responsible for the emotions? And we did that, for example, for emotion happy. And here you can see that we can add the constant to every frame. And this is the same video, but we added those happy betas to this one, and we subtracted this from the first video, and you can see that it looks pretty scary, but it somehow works, because here the face is always smiling, and here with closed eyes, and here we have opened eyes and closed mouth.
Yeah, so oh, sorry, it's not the original, right? This is
this is original. We've subtracted betas.
Oh, this is those are the opposites. Yeah.
Yeah. So we only did that to check whether those betas have some semantic meanings, and you can see that
it didn't have to be pretty. It just had to, like, prove that, like, you are able to manipulate the output in such a way. Yeah. So the next step was literally adding emotions, like adding emotions to video, and yeah. So as we've said earlier, there is this network for expressions, and basically the goal was to forget about this whole training part, just use the same weights that the authors used, and just modify the output as it is. So train the model to detect some emotion vectors or something like that.
Yeah, so we just wanted to add something to those betas, but not constant. We just wanted to train the model to generate those delta.
That's the next step. Yeah, and actually, like if we, oh sorry, why don't they? Yeah, okay. So this is one of the first. Yeah, so like
this is linear regression.
Yeah, so this is basically linear regression. It was supposed to be angry, but like it didn't work out. Yeah, so this basically used this model used the previous like 10 frames or something, betas from the last 10 frames to predict the emotional betas for the next frame. So I'm using linear regressions. Actually, this was a really long shot, but in this approach, we hope that positional encoding used in transformers could be used to kind of treat it as translating sequences, translating the sequence of frames into a sequence of emotional frames. But like as we can see, it actually underfitted, even with like even with a big enough number of parameters, like 8 transformer decoder layers or 16, I think it was in this case. Like it's still underfitted, so the model basically couldn't didn't understand the lid motions, even though it had access to it. Basically, the model was punished to like for any deviations from the standard mouth position. So it chose to just don't move them at all. Yeah. Oh, actually, this one was purposefully overfit. But yeah, using even more like even more layers. So yeah, it's a very delicate situation. Actually, there is it's maybe not very practical, but like the idea was the next question was, what if we increase the you can interpolate between the original vectors from the original model and the angry ones from our model. And you can also increase it beyond 100% and see what happens. Yeah, this is the... yeah, this produces actually really funny results. So this is like... oh, sorry. This is like... minus 300% angriness, and this is 300% angriness, and those are 0 and 1. Oh, sorry, yeah. So this 0 and 1 are not. This is actually this frame is the original Sat-Stoker output, which, as you can see, is indeed quite blunt and emotionless.
Yeah, all the outputs from the Sat-Stoker are just emotionless.
That's the entire point. And other approach would be to use like orthogonal projection. It's actually really interesting that you can manipulate emotions as a linear vector space. Yeah, but it also produces like similar results. This is minus 300%. It's 300%. This is 100%. Yeah. So also, yeah. No,
as you can see, those results are not very subtle, and it's hard to pick the right coefficient to just multiply it by 300% or minus 300%. So what we wanted to do was just fine-tune the XNet for each emotion separately and have just separate models for all of the emotions from our set. It was not a lot of them, so we can do that. And the very important assumption is that we cannot increase the inference time because it has to be generated in real time. So set talker generates in real time, and we couldn't add many new layers to this model, and so we just fine-tuned the XNet for each emotion separately from our data set that we presented earlier. And
actually, sorry, I will just add that it's not that we haven't tested different values between those -300 and 300. It's just that the results was pretty much what's expected. Like it ranged from caricature to bland and neutral, and then to another caricature. So it wouldn't, like, changing it to, I don't know, 150% didn't really solve any problems. Yeah, so that's the, I guess, question I have skipped.
Okay, and in this approach we assume that we have grand truth, because authors of the paper assume that we don't have to have the grand truth because we can generate it using wave to leap, so we didn't use wave to leap. We just use the grand truth, which is a better approach, because in grand truth we have those emotions, and in wave to leap we don't have the emotions.
Yep.
And but you can see also that in this case, this is the original video, and this is a video that we generated. It solves some small problems, like this person from set talker just nearly don't open his mouth, and in our case it's quite better, but still we have some underfitting, which was our main problem during this whole project, because set talker is a very large model, and it's hard to...
Main theoretical problem. I should point out that the code was pretty pretty bad.
And we also had to fine-tune the second model used in this, the second small model in this set talker, which is called pose VAE, because when we had those stronger emotions, the position of the head was wrong, so we also had to fine-tune this part.
So you can see that the motions are not that prominent, but they are, I'd say, more natural.
Especially when the head is moving for the original set talker, you can see that those movement is not, it doesn't look natural. So the conclusion is that those vectors from this feature space have semantic meanings, and by changing distributions of betas, we can influence the emotions. By moving them by a vector, we can have influence over the intensity of the emotions, and we can somehow improve set talker without increasing its inference time. And that's all.
Thank you.
Thanks.